Good afternoon, everyone. The Atoms Group is pleased to have Professor Escobedo for today's seminar. Professor Escobedo is principal investigator at the Escobedo Lab at Cornell University. Professor Escobedo leads research on the development and application of simulation and modeling methods to elucidate the connection between microscopic structure and macroscopic properties of polymeric and colloidal materials. Today, he's going to present about some of his works in this seminar entitled Developing Engineering Principles and Tools for the Self-Assembly of Nanoparticles and Oligomeric Materials. Thank you for being with us. Please go on.
Okay, thank you for the introduction. And also thanks to the organizers for inviting me and giving me this chance to share with you in this interesting time some of the work in my group on trying to develop some of these tools to study self-assembly in nanobuilding blocks. So I guess in a broader context, this work pursues this new chemistry of nanoblocks, where the idea is that now we can design these larger objects in the range from 1 to 100 nanometers, where we can change not just the size, but also the chemistry and the shapes of these particles in multiple axes of variability like patchiness and isotropy. And so this plot shows some example of this axis of variability. Let me use my pointer here. And in our group, over the years, we have explored a number of axes of variability as well as the ones shown here. You can see some of them are sort of rigid particles, some of them are actually soft polymers, and some are hybrids. But in all these cases, the key question is, how do you design these objects so that they will assemble into some structure that is desirable with some order? And not just for single components, but also for multi-components. You will have some energetic and entropic knobs that you can play with. And in some cases, you can harness some of these transitions to, for example, have some structures that can reconfigure, like if you want to create a synthetic chameleon skin that's in 2D, or for example, a responsive nanoporous membrane, with there's a collaborator that, for example, can make these very interesting membranes with block of polymers whose pores can open or close depending on the environment. So in any case, it may be that we're interested just in the thermodynamic stability, but beyond that, there may be other aspects that we want to optimize. Now, it could be kinetics, could be some type of structural order, or some property that will be important for the applications such as the ones listed here, electrical or photonic. So in this context of this idea of going from some novel building blocks that can give rise to new or improved properties through phase assembly. So let me just give you one example where new techniques experimentally can allow you to create, for example, with high precision and monodispersity, different shapes within this truncated cube family that goes all the way from cubes to octahedra. It's known as the modified polyol process. You can produce cube octahedra as well. And people can make them of different chemistries, different sizes. In this example, one of our collaborators makes these quantum dots or nanocrystals that are really tiny, order 2 to 10 nanometers, that happen to have some of these shapes, and he wants to assemble them into active layers for solar cells. And of course, how they assemble is going to determine the efficiency in these devices. So in this talk, first I want to talk about the idea of using nanoparticle shape as an engineerable feature to create multivalency and self-assembly. And with the main idea of trying to postulate some general variational principles that will allow you to optimize the co-assembly in binary solutions and compounds. And in the second part, I will be talking about now sort of creating mesophases from oligomers and ball amphiphiles, especially to create these very interesting network phases that can have very appealing ion electron conducting properties. So for the first part, one of the motivations was This classification scheme that people in metallurgy have to describe different kinds of solutions, or crystals. So in this case, it's illustrated for two components, here shown in red and yellow. And so I'm just going to classify them as being type 1, 2, or 3, so different kinds of alloys. So for the rest of the talk, I will not be really concerning myself with type 3, these interstitial alloys, only with the type 1 and 2. And so what you see in this alloy, in this example in 2D, I have two components and they're forming the same lattice. So that's the same. What is different is that in this case, type 1, the two components are sort of randomly distributed in the space, while in this case, the components are intercalating in a very precise manner. So type 1 is known as a substitutionally disordered alloy or a solid solution, while type 2 is known as a substitutionally ordered alloy. We could also call it an intermetallic or an stoichiometric compound or even a salt. Now, it turns out that for different kinds of materials, there are some semi-empirical rules that people have come up with. For example, for metals, is the Hume-Rothery rules. For ionic salts, the Pauling's rules that allow them to sort of guide the design of these different materials for salts. So it would be really nice if one could do something like this, but in the context of nanoparticles. So a metallurgy of nanoparticles, if you wish. Now, when it comes to spherical components, either atoms or nanoparticles, there are lots of papers, lots of groups that have worked on this problem. So in that aspect, I think we are more or less covered. But if you now introduce shape, for example, if at least one component is a polyhedra, then there's not really much in the literature. There are some significant effort when it comes to pure polyhedra. And these are some of the groups that have worked on this problem, including our own. But as I said, for mixtures, there's much limited information. So and that's the focus of this presentation. Now, if I'm going to come up with some rules, the rules are based on the interactions that these particles can have. And I can classify them as being, for example, energetic interactions. If you were to use electrostatic charges or multipoles to create interactions, or something that's been used a lot nowadays is this complementary DNA strands that are grafted to different particles to create selectivity. We can also use entropic interactions, like depletion attractions. We can also use the conformational entropy of the chains. So chains hate to be stitched because that will reduce their entropy. So that can drive the system to move into some preferential structures. But as I said, we want to also emphasize the shape of the particles, the idea that as you increase the concentration, there may be some preferential structures that are being formed by what's known as packing entropy. So that creates a sort of directional bonds, and depending on the number of facets, for example, a valence, and which is based on shape complementarity between the particles. So for my analysis, I wanted to sort of simplify things to the bare bones and basically describe the kinds of disparities between the two components by using two scalars. Although in general, you will need many more, but to simplify, there will be one that we'll call entropic, and it will be represented by this symbol zeta. So here, the ratio of the characteristic lengths of the two components, L1 and L2. There will be another one that we'll call the energetic asymmetry. There will be either chi or epsilon. I will use this interchangeably. And that basically tells you, what's the disparity between the unlike contact versus the like contact. So that will give you a sense of energetic selectivity. And so the idea was that I wanted to understand what will be the changes in these parameters that will lead to an optimized formation of either type 2 or type 1 or 2 alloys. Now, to model, for example, the interspecies attraction, if you are thinking about using these grafted DNAs, one thing to keep in mind is that the interaction will depend not just on the distance between the center of masses of the two objects, but also on the degree of alignment between the facets. There will be something like this delta parameter here that when you are really well aligned, delta equals 0, you will have the stronger attraction because all chains will be engaged, while if delta is large, this interaction will decrease. So these effects can be captured by explicitly modeling the chains, but it will be very expensive if you are dealing with thousands of particles. So another way you can do this is by using a polybead model, where you will have these soft beads at the skin of these particles that will have this interaction that sort of will mimic this hybridization interaction. And this is a model we have explored some years ago. But for this, we wanted to have something even simpler, to coarse grain this into what amounts to a directional square well potential. So the idea here would be that it's only when the particles are at the right distance and the right facet alignment that you will enact an energetic attraction, a contact energy of value epsilon. One advantage of this is that numerically, this will be identical to this chi parameter I was telling you about in our generalized framework. So just keep this model in mind in the future when I introduce attractions. So for our simulations, we were interested in the mesoscale behavior, so thousands of particles assembling. So for that, you're justified in using a coarse grain model and implicit solvents. Now, for the most part, we use Monte Carlo methods, and of course, we faced a number of challenges. For example, identifying some of these phases and phase transitions. We will need to use a special method, for example, to detect overlaps, quantify order, or measure free energies. Now, in many cases, we can just use methods in the literature, but oftentimes we had to modify them or even introduce novel variants to be able to make these calculations more efficient. I will not really have time to explain much of this methodology, but we use extensively, for example, this free energy extrapolation method that we call Phoenix to trace phase boundaries that will be essential to create phase diagrams. So let's go first to this type 1 alloy that we call it a substitutionally disordered alloy, and consider the following question. If you were to have two particle shapes which are completely thermal, so there is nothing energetic that's going to help you with this, and they form very different lattice structures when they crystallize, would they be able to form a solid solution? If you think about this question, you may come to the conclusion that that seems unlikely, given how different they are. And you wouldn't be wrong. I'm going to show you just one example for an isothermal mixture of spheres and octahedra. So these are different shapes. They crystallize into different lattices, FCC for spheres, this Minkowski crystal for octahedra. So let's see if they are able to mix. So this is an example of a phase diagram showing the osmotic pressure here as a function of the composition mole fraction of octahedra. And so this shows that this is a type of diagram known as eutectic diagram. And all the regions in gray are basically depicting the two-phase regions where basically things phase separate, so there's no solution there. This is the isotropic phase over here. Now, this region in yellow corresponds to a solution where the Minkowski crystal is dissolving some amount of spheres. You can see that it can dissolve up to about 9% of spheres in it. But if you look at on the other side, you can see that the spheres in the FCC crystal are basically unable to dissolve any of the octahedra in there. So it's a very anisotropic thing. There is some amount of solution behavior, which is what we want, but really very limited. But this, not given an thermal system, should be very affected by entropic considerations, so which are embodied in our parameter zeta, this size ratio. Now, this phase diagram was found for this particular choice, where the sphere diameter was about 0.84 the octahedron edge, which is a choice where that will give you that the transition pressures from isotropic to order were the same for the both components. You can see that it's about 7 here, also 7 over there, that we thought would be advantageous, but clearly wasn't. So we needed to optimize this. So how can you do it? So coming back to our framework, one of the key questions was, what is the quantity to optimize? And given that we don't know really a priori what's the composition or the composition range that the system may attain. So it was a rather open question. And for the longest time, we thought that we needed to come up with some geometric rule that would be very clever and very cute, but they were not as robust. It was only after a while that we realized that thermodynamics had the right language to describe things to optimize. And that language is, of course, free energy. So the question was really, what free energy needs to be optimized? And so we settled on the following, that we wanted to optimize the free energy of mixing. But not knowing the composition, it was best to try to do this at the infinite dilution conditions, meaning that if I have this two phases for the pure components, I want to maximize, for example, how welcome this phase will be to the other component. And so you can measure this by introducing these virtual mutations, where you try to change a host particle into a guest particle, but you do that in both solid phases, and you add them up to create a quantity that, as I said, more or less represents this free energy of mixing at infinite dilution. We will call this the exchange free energy, delta Fx. And we postulated that if you minimize this quantity, you will find the optimal conditions for these parameters, zeta and chi. And the idea then is that that will maximize the substitutional symmetry of the two components. So let's see how that works for the example I show you of spheres in octahedra in this thermal mixture. This is this delta Fx as a function of the size ratio, the ratio of diameter of the sphere over the octahedral edge. And it clearly shows that there is a minimum there for a value of zeta of 0.96 about, which is different from the one I showed you before. Now this equal ODP that happens to be over here. So let's see how our phase diagram looks now. So now it looks something like this. So now you can see that, for example, on this side, the Minkowski crystal, the octahedral rich crystal, can dissolve much more on the spheres, almost 20%. But also importantly, on the other side of the diagram, now you can see that the FCC crystal of the spheres can dissolve up to 20% of the octahedra. So, and that's great. That's really what this rule was designed to optimize. But we also got the surprise, something we did not expect, that in the middle, we found also this region of this phase R, which is also a solid solution. And if I were to show you some pictures of that, two compositions, you see that the octahedra are not orientationally ordered. That's why we call this a rotator phase, the symbol R. But more importantly, that the lattice structure is different. It's different from the parent crystals, not FCC, it's not Minkowski, it's a BCC structure. And so it should be pointed out that we did not optimize for this phase. We didn't even know that this phase existed. But because we optimized the substitutional symmetry of the two components, somehow they found a new solution, a way how they could coexist in a solid solution behavior, so which we found really interesting. Now, this may be a good point to try to ask the question, how about an intermetallic compound? So in this system, I could have expected to see at the equimolar composition this cesium chloride structure that corresponds to a compound that will look something like this. And at least for this size ratio and for the pressures we could simulate, we never saw this structure. And that was a little bit disappointing perhaps, but not very surprising in the sense that to get something like this, it has to be true that each component really prefers to be contacting the other component. You can see that the octahedra will be touching basically spheres, not octahedra. So that clearly needed some strong selectivity to do something like this. So we thought, oh, that's time to turn on our energetic attraction. So I'm going to now change epsilon or chi. So first, let me show you the phase diagram that you will find for a size ratio of 1 and epsilon 0. So it's a thermal. So similar to what I showed you before, we found this R phase right in the middle. Now I'm going to change epsilon to be 0.75 kt. So you see that there is a significant change in the phase diagram. In particular, the phase that appears in the middle is no longer this phase R, but another phase that I'm calling C star. And if I show you a snapshot of that, you can see that this is a compound phase. And indeed, it corresponds to the cesium chloride lattice that we were expecting. Also because that system had been studied before by using this sort of DNA graphs to create this energetic selectivity. So it was comforting, I guess, that we were able to go from basically a substitutionally disordered phase to one that contains substitutional order. Now, interestingly, both are BCC lattices, just that this is substitutionally disordered, this is ordered. So one can argue that we changed the type of alloy by defeating the mixing entropy that we had maximized by introducing epsilon, this energetic contact per facet. But I have not really optimized these compounds yet. So I'm showing you that we needed epsilon to create a compound, but how do you optimize it? Now, compounds are very interesting materials, of course. They're at the forefront of materials design. Names such as zeolites, clathrates, and perovskites are really at the forefront of applications. So it would be very interesting if I could also create compounds like this by using these nanoparticles and using shape as a knob. And for example, not for these two different cases. So you will ask the same question. Now, what figure of merit to use? And so one key simplification that was not there before in the other type of alloy is that now we have just a single composition. So we know it's just the stoichiometric composition, which, for example, in these examples will be the equimolar case, right? So that simplifies things a lot. And again, we can sort of phrase this question as to what kind of free energy we need to optimize. And one can argue that, well, it should be the free energy of the compound. It's almost like a single component system or pseudo one component system. So imagine that this is a phase diagram in general terms. This zeta is some design parameter. And this region in yellow is where this compound C star phase lives. So surely there should be some point inside where this free energy is a minimum. So I just need to find it. There will be some place inside this yellow region. So that's just a search I need to do. But in this diagram, I'm using this parameter eta here to represent a thermodynamic function that will favor order versus disorder, excuse me. So meaning that this eta will be either pressure or reciprocal temperature, so that for high values of that, I will favor the ordered state, and for low values of that, I will favor either the isotropic phase or some other phase with lower degree of order than the C star phase. So there will be a boundary that comes between these two phases. Now, if you look at this equation, which is just the fundamental thermodynamic equation for the Gibbs free energy, you will see that the coefficients, volume and entropy T squared, are always positive. So that tells you that the free energy can only increase as you increase along any of these two axes eta. So what that means then is that you don't need to be looking for the minimum free energy everywhere, but only along this boundary, right? And this also makes practical sense, because in practice, if you want to access the C star phase, it will be from the isotropic state, and trying to get to that through some kind of crystallization. So we just need to map the free energy along that boundary and find the place where it's minimum. And of course, the same idea will apply for if I had multiple design parameters, just need to basically find that point in that phase boundary as shown over here. So to give an example for the same system I was telling you before, so octahedron spheres, and these results are going to be for the stoichiometric composition only, and for a fixed value of epsilon. So epsilon is 0.75 kt. So this is a phase diagram showing the volume fraction as a function of zeta, the size ratio, diameter of a sphere over octahedral edge. So the C star yellow region corresponds to the compound. The isotropic phase lives down here. This is the two-phase region. And you can see that, so this corresponds to the C star phase for relatively small spheres. This corresponds to the case where the spheres are relatively large. And you can perhaps ask whether you can detect, well, first thing is that these two things are the same crystalline structure, so that doesn't change. But maybe the one that's more ordered can tell you something about their stability. But we tried, for example, by using G of R or the structural factor, and that seemed to be very tricky and highly non-trivial. Our metric, so what we propose is that if you look at the coexistence free energy along this boundary, which corresponds to this curve, just need to find the minimum. In this case, that corresponds to about 1.25 zeta. And I can show you what the system looks like. It looks like this. Now, visually, there is an observation I make that if you look at this case, when the spheres are small, so what I see is that the large octahedra are touching each other neighbors in creating small gaps where the smallest spheres nestle. While in this other case, for larger spheres, it's the other way around. Now the largest spheres are contacting their neighbors and creating small gaps where the small octahedra nestle. Now in this phase, it's different. So for the optimal case, what I see is that neither one is dominating, sort of both are contributing equally in contacting neighbors and basically creating this geometry in this structure. Of course, that's just a human interpretation. In reality, what thermodynamics tells me is that it's really this free energy that determines what structure is more stable. So it's this. And it's a calculation you can also do in 2 dimensions, here shown as a function of not just zeta, but also the epsilon. And expectedly, you can see that the free energy decreases as you increase epsilon. So that makes this contact energy more favorable to the compound. But also interestingly, as you increase epsilon, you go from having just one solution in zeta to having 2 solutions in zeta. So there is a bifurcation someplace, which is kind of interesting as well. So with that, let me summarize what I told you in this part of the talk. So for these 2 types of alloys, we've identified, we postulate these general free energy quantities that would be the metrics to optimize that behavior. I've shown you results for this test bed. I didn't show you results for this other test bed of cubes plus spheres. One key difference is that in some ways the valence or the coordination number of the lattices changes from being 8 here to being 6 when you use cubes. But the main results, the main conclusions are the same. So in this case, we don't see this unusual phase in the middle, this R phase that I told you before. This is more of a normal expected result, I guess. But so this system has also its own story that I won't be able to tell you today, but maybe you can read about it. So we have introduced these metrics to co-engineer both entropic and energetic interactions that I posit should be generally valid. So we have validated them for coarse-grained systems, but there's no reason why they shouldn't be applicable to atomistic models. More likely, the main complication is that now these parameters will be multidimensional as opposed to just being a scalar, and should also apply to multiple components. So as part of our ongoing work, we're also trying to create open lattices, which tend to be more challenging, but also more interesting for due to their optical properties. Another question is whether we could selectively, or excuse me, if we can create this selective attraction, not energetically, but entropically. That's something Isabella, for example, has been exploring, and we have something to say about that. And also the fact that everything I said is for 3D systems, but there are many instances where you can create 2D or quasi-2D systems, which are very interesting. We have collaborators that use different methods to assemble basically monolayers, and they also create very unusual, very interesting structures that I won't really have time to talk about it. So finally, we're also very interested in optimizing kinetics, because it will not matter if, for example, you predict some very interesting phase to be thermodynamically stable if kinetically it's very hard to access. So we're looking into these questions, and I won't really have time to talk much about that. So let me just briefly give you a flavor of what we are doing. So you can measure rates, or you can also measure as a surrogate for rates this free energy barrier. So this is free energy as a function of, say, the nucleus size of the solid phase. As you go from the metastable liquid to the stable solid, so the height of this barrier will tell you, something about the kinetics. If it's large, that means that there's more difficulty in going from here to there. Now you can compare this kinetic rates by comparing systems for the same driving force, and the driving force is this degree of supersaturation. So let me show you just some sample results for a fixed value of this supersaturation, and we can take as sort of reference hard spheres. So for these conditions, hard spheres will have a relatively large barrier, so the assembly will be somewhat slow. And we find that there are some systems, there's some pure polyhedra, these are all hard, that can actually assemble much faster. So have faster kinetics, and there will be some other shapes that actually have much larger barriers, so will be much slower kinetics. And I think we understand why, and there are some of the papers where you can read about it. But there are also some systems that we are still trying to understand. And one of them is the case of cubes. That would seem to be one of the simplest ones. But what happens there is that it may be that the system does not follow a classical nucleation pathway. So if I were to show you just the hard spheres, this is a very dense system, but you are just seeing the spheres that are forming the nucleus, so the crystalline nucleus. So what you will see is basically this sort of consolidated shape of the nucleus. Well, if you try to do the same thing for the case of cubes, you won't see that. So you basically see small nuclei forming all over the place, coming and going, and eventually they consolidate into a larger cluster. So it looks a bit like a spinel decomposition, but it's not, because it also happens when you have large free energy barriers. So we're still trying to understand this, but it resembles a lot a percolation transition that's sometimes seen in some polymer systems that form networks with multivalent cross-linkers. In our case, we have perhaps these weak reversible bonds because they're entropic, but something that we have found recently that we think is going to be key to explain this behavior is the fact that the interfacial free energy between the solid and the liquid is very, very small compared to that of other systems. And we're still trying to understand why this is, but I think that's going to be a very interesting story once it's completed. So I think I'm ready to move to part 2, unless there is maybe a quick question on part 1.
I do, actually.
Sure.
My name is Felipe. I'm a PhD student at the Federal University of Rio. I was wondering if there's any mapping that you can do onto, because if I understood correctly, polymers are like coarse-grained into a cube, and the interactions are is there any mapping on the chi parameter of the Flory-Huggins theory that you can do? Is there? Do you know if there's?
Yeah, so in some ways, that's the idea that. So what we are saying is that when there is a contact, the full contact between the facets of two particles, then that corresponds to basically chi. So this contact energy, when there are full contact, that's epsilon, which by arrow mapping, that corresponds to the chi parameter. It's a coarse-grained representation. You can make it more refined, and we also have some models to describe this in a more refined matter. But so this allows us sort of a quick mapping of these phase diagrams to really understand whether, or test whether some of these ideas we had about optimizing compounds was in the right track. But for sure, those approximations can be made more rigorous.
Okay, thank you.
Welcome.
Fernando, can you play a, sorry.
Yes.
Can you play again the crystallization of cubes?
Sure.
It's very interesting.
It is. It's very. So So there I'm trying to just plot the largest cluster, and the largest cluster just comes and goes, doesn't stay put. And we believe that connects to this low interfacial free energy that allows them to dissolve very quickly. But at some point, there are enough of them that they percolate and form this sort of one-phase behavior.
Thanks. Interesting. Very.
Welcome. Okay, so let's move on to the second part that has to do with now the assembly of these oligomers, which are multi-block. And the fact that they are multi-block gives them additional functionalities because each block can contribute to some specific property. Also, just like in the case of nanoparticles, nowadays there are synthetic methods that allow high control of the sequence and the topology of the molecules. Now, compared to polymers, the fact that these are smaller size implies much faster assembling dynamics and annealing of defects. So they clearly have a kinetic advantage. And there are many interesting materials out there that people explore, but for this talk, I will just be concentrating on these ball amplifiers. So I'm a part of a team that has 3 other groups that do experiments, synthesis, characterization. You can read about us in this webpage. But our goal is to design a single soft material that will be able to conduct both ions, like lithium, say, through hydrophilic domains, and electrons through, say, pi conjugated domains, so that this can be used for batteries or biosensors and so on. In fact, that corresponds to the holy grail in biointerfacing, because if you think about it, in the biological realm, signaling happens through conduction of ions, while in the electronic domain, it happens through the conduction of electrons. So having a material that can do both will be extremely useful. So for that purpose, this is one of the molecules we've studied. I'm going to show you results about. You can see it's a linear tri-block that has a sort of rigid block in the middle, which is hydrophobic. It's pi conjugated, has these thiophene rings. And on the sides, you have these more flexible hydrophilic polyethylene oxide domains. And so our collaborators were able to synthesize, prepare the films, and characterize them in multiple ways, such as, for example, using wide-angle X-ray spectra to see a structure. Now, we wanted to do also simulations. In fact, the simulations preceded some of these experiments. But it turns out that if you just use molecular dynamics and you throw into a box hundreds of these molecules using an atomistic force field, you can wait months and almost nothing happens. It doesn't assemble. So the time scales are really off. You need to do something about it. So the thing we did was to first coarse grain this material so that it can assemble much faster. And once it assembled, then we can reverse coarse grain it into a fully atomistic model and then relax that system fully so that we get the structure to compare with experiments. And it shows something like this. So you can see in the blue domains are the thiophene rings where the electrons will conduct. In red are the domains where PO sits and the ions will conduct. And now in comparing our structure factor to theirs, there was a doubt that they didn't know exactly what these A and B diffraction peaks were. So they knew what these peaks over here were, which are the same here. Those correspond to a layered structure. So that much we know it's a sort of lamellar phase. Now this A and B could be easily seen in our simulations. And they corresponded to 2 key distances between these thiophene ring columns that form. And those distances are characteristic of the so-called herringbone packing. Now this packing is how thiophene oligomers crystallize. So what this was telling us is that in our structure, these blue domains are sort of crystal-like, while these red domains, now we can also see they were liquid-like. Now this is a very interesting material because if you think about it, you have this perfect intercolation of these nanometer thick layers of liquid crystal that would defy classification as a solid or liquid. But so that dual characteristic is actually great for our application, because if you want to conduct electrons, you rather do it in a crystal-like material, because electrons are conducted by this sort of quantum mechanical effect of resonance or particle in a box. While if you want to conduct ions, they move basically through Brownian motion, so you want an environment that's very mobile, very liquid-like. So this structure turned out to be great for the application, and in fact, we have measured that. They have also measured this, and we found that it has excellent dual conductivity that's better than any other material that has been produced so far. So we're very happy about this result, and of course we want to optimize it. One way would be perhaps to explore different lengths of these blocks. But more than that, we wanted to also design 3D percolated network phases, because that would allow us to have conductivity in 3D, not just 2D as a lamellar phase, and also because these phases, these network phases, are more robust to the disruptive effects of defects or grain boundaries. Like in the lamellar phase, a situation like this will basically kill any conductivity. And finally, that, as I told you, one reason why people prefer polymers is because they have stronger mechanical properties. Small molecules do not. But if they assemble into these network phases, they will also have very strong mechanical properties. So clearly this will be ideal. And there are some oligomers, like the one shown here, which is known as a ball amplifier. And you can see that it contains 3 chemical groups shown in red, these glycol systems. You have this biphenyl rigid core in the middle, and you have this side chain, which is sort of perfluorocarbon. So these two are hydrophobic. This one, the red, is philic. Now, this material has been shown by experiments in simulation to assemble into this structure, which is using basically the color scheme in this coarse grain representation. And that gives you an idea of this sort of 3-dimensional structure. So this is known as a gyroid, as a G phase. In this picture over here, I'm showing things without lateral chains, just to make it simple. From now on, you will not really see the lateral chains. But you see that these struts have 2 different shades of blue to underlie the fact that there are really 2 networks that are sort of interweaving each other, but they never touch and go sort of forever in 3 dimensions. So a structure like this will be ideal, but it turns out that this chemistry is not best for this dual conductivity we're after. So clearly we'll have to change the chemistry. But beyond that, we wanted to understand why this molecule forms this interesting phase, right? And for example, understand to what extent it's all about energetics, or perhaps entropy also plays a role. So to answer this question, you can just put these different molecules in a simulation box and see how they assemble. But if you do it, you will find that oftentimes you get different phases that form spontaneously, right? So there are multiple candidate phases, and so it would be hard to tell which one is more stable thermodynamically, unless you're able to measure free energies. But how do you do that for phases of this sort, that are really examples of phases that are formed by amphiphilic molecules or diblock copolymers, as shown here? And amongst these mesophases, the G phase I told you about will be one of them. So these materials, as you can see them, they are not really liquids. They are also not solids, although sometimes people call them solids. And even though my group had expertise in advanced particle insertion methods, they were unsuitable to measure chemical potentials in these materials, because they are sort of like crystals. What you needed to do was use some form of thermodynamic integration. In this case, you wouldn't be able to use an Einstein crystal as your reference state. You need to use something else. But so drawing from the ideas of Groschola and Mueller, for somewhat similar questions, we have sort of advanced a method that will be, we think, very useful in computing free energies for materials of this sort. So just to give the key idea, so imagine that this phase over here is the phase that you want to compute the free energies, an order phase. Here you're just seeing, say, the rod part of the molecule. And so you're going to use the disordered state as your reference, which is here. So in some phase diagram, say these are no two thermodynamic parameters, this maybe say density, this is something like, say, beta, the reciprocal temperature, so that for low values of beta, you have a disordered state, and for high values of beta, so meaning low temperature, you have the ordered state. So one way how you can get the free energy change between these two things is by basically going along that line. But if you do it either in one direction or the other, you will encounter huge hysteresis because it's a first order transition. So, and it's such that you won't be able to get a reliable free energy difference. So this doesn't work. You basically need to go into another dimension. So there'll be another axis, let's call it lambda. And the idea is as follows, that given that you create this interesting geometry, you will use this to cast basically a mold of an external field that is going to basically bias the system into going into that structure. So you can do that by creating a granular field where you will use these Gaussian beads that are going to selectively attract the rods, because we know that the rods go into those regions. But you are going to sort of increase this potential in a gradual way. So we're going to modify the Hamiltonian by adding basically this external field, this UG that corresponds to these interactions. And when you turn it on, you're going to do it very gradually, so that it goes basically from a structure that looks like this, disorder, to something that looks like this because of this bias. But you have to make sure that this change is reversible, or else it wouldn't work. So once you are there, basically something that resembles the ordered structure, you can turn on the interactions, say by increasing beta. And finally, of course, you'll have to remove the field gradually. So once you add the three contributions, 1, 2, and 3, you'll have the total free energy difference between this phase and that phase, which is what you want. Now, if there is another candidate order phase that forms, let's say the cylindrical phase, then you repeat the same process again, and then you will compare the final delta Fs to see which one has the lowest free energy in the order state. So that's what we'll do for our wall amplifiers. So, and we're going to use for these calculations a coarse grain model that we found by a top-down approach. So we find the interactions by making sure that they reproduce the experimental behavior that has been seen for these molecules when you have a linear chain, so when the things look like this. But our goal was to explore what happens when you make the lateral chain bifurcated, or it's known as swallowtail. So let me show you some results. So first, for the case of a linear chain, so I'm going to change the number of beats in this lateral chain. In the snapshots, you are not seeing these beats in yellow, just for clarity. So it shows that for these choices of n, you form this lamellar phase. So the yellow chains are going to be inside these empty regions. Now, when you make n smaller, you start forming very interesting columnar faces with some sort of polygonal cross-section. In this case, you can see that there's a hexagonal cross-section. So these are the faces that we use to validate our model by comparing to experimental data. So now we wanted to see what happens when you make the lateral chain to be bifurcated. Now, in some ways, this is a relatively minor change because everything is the same, all the interactions, number of beats, and so on is the same. And yet, when you calculate the phases for intermediate temperatures, what you find is this very different. So as you can see, for these examples, the phases are network phases. What you see over here is this G phase I was telling you about. But we also find, for example, this single diamond phase, which is a phase that was predicted, and it was only 2 years later that they experimentally confirmed our prediction. And you can see here that, just to simplify the skeleton, for you to see that they have these very interesting network structures. But so the key question would be, why is it that such a big difference, given this small change? And so one of the explanations is physical in nature. It goes as follows, that if you look at these cases where the lamellar phase forms, so the rods are packing into these layers, and the chains are going to extend to fill up this sort of rectangular volume. And if you make n larger, they can just extend farther into that region. But if you make them bifurcated, now it's the exact number of beads. So that means that they need to occupy the same amount of volume. But now, because they are shorter, they cannot extend farther from the interface. So they have to find the same volume, but they will do it laterally. You have to find it around them. And the only way they can do it is by curving the interface, creating basically eventually tubes. So once you have formed tubes, if the tubes intersect, that's when you create these network faces. So now this explains qualitatively why we see these changes. But to see things more quantitatively, you have to, of course, measure the free energy. And I'm going to show you an example where we basically look at this case, now this swallowed system for this n value that can form the L phase or the G phase. So what we find is that the G phase at intermediate temperatures is the more stable. But when you look at the energetics, we find that the lamellar phase has the lowest energy. So that should be energetically favorable. That makes sense because, so being the interface is flat, you have no less interfacial penalty. But we found that this phase has the lower free energy. But combining these two results and the definition of the free energy, these results are only consistent if the G phase has the higher entropy, because that's what contributes to this, and that's what lowers the free energy of this phase. So where is this entropy coming from? It has to be coming from the chains, not these lateral chains. And indeed, if you look at the end-to-end distance to see what's the average extension, you will find that these chains, if you put them in this lamellar phase, they will tend to be too stretched. And I told you that chains hate to be stretched because that increases their, or excuse me, that decreases their conformational entropy. They want to be more relaxed. And it's in the G phase that they are more relaxed, kind of like in the isotropic phase. So this explains the source of this higher entropy, and also shows you how you can use entropy to create a structure with, in some ways, more order, because this seems to be more order than this. But also you can notice that if I were to change temperature, I can basically kill the contribution of entropy. So at some point, T will be low enough that basically the free energy is dominated by energy. At that point, then the lamellar phase should be more stable. And indeed, that's what is found in simulations and experiments. So I think this example shows you how you can tune the effect of entropy by either the design of the tail or by just changing temperature. So before I finish, I want to give you a quick overview of some ongoing work in our efforts to try to also optimize the kinetics in these transitions. And again, will be a case where you need to either compute rates or these free energy barriers I was telling you about. And one key limitation here is that you need to have order parameters to be able to track the nucleation of these order structures, which again is not something that has been found or has been done before. For phases of this sort, how do you do it? And one question you can ask is that you cannot do this at a sort of atomic level, because if you are an atom, would you be able to tell if you are part of a region where incipient order is forming, where this nucleus is? So you will find that that will be almost impossible. But patterns are recognizable at the domain level. So using this insight, what we did was then to try to basically, for the analysis, bunch the actual segments or atoms into a much coarser representation so that each bead was about the size of the domain. So you will go from something that looks like this to something that looks like that. And once it's like this, it's a lot easier to see whether there's any pattern in the way how these two different blocks are forming. So we use this idea, and let me just illustrate for one case when we formed this network phase called the diamond with this Bolamphy file. So you see that the red beads in the molecule tend to bunch in what will become the nodes of this network. So that if I were to replace the nodes by just a bead, and I look at the position of the beads, then I can see whether there's a particular coordination of these nodes. And to look at that, there are already known order parameters, like this is Steinhardt order parameters, that allow you to basically pick out whether there is some symmetry in the way how these different particles bond, in this case, how these different bonds or these different nodes are connected with other neighbors. In our case, we'll use something like known as Q4 because I can detect this sort of diamond symmetry. And when we look at now how this phase forms at some conditions, we're going to do a mapping where this sort of structure is simplified into something like this, where again, all the bits in the node are represented by a single bead in red, and the struts, which are usually a bundle of rods, just mapped into just a single rod, just to make things simple, so that if it has the right symmetry, so if you're seeing this sort of tetrahedral coordination, they will look something like this. But if they are not, so you have a different kind of symmetry, I will show the struts just by dashed lines. What you find is that from the beginning, very quickly, the system basically forms a network, but it's a disordered network. It's just all made of these struts, as you can see. And it's only after a long while that you start nucleating the ordered network. You start picking out this motif that will start growing and growing, and eventually will overtake the whole system as shown here. Interestingly, this disorder to order network transition resembles a lot what happens to water when it nucleates into ice through hydrogen bonding. So anyway, so now we're in the process of looking at free energy barriers for the system and others. So just to conclude then, I hope that you appreciate that these oligomers are a good platform to produce 3D phases. Some of them we predicted before they were realized. We have introduced new methods to try to assess thermodynamics and kinetics. And we're also, of course, looking at an inverse design to be able to specify chemistries for these dual conducting properties. So with that, let me acknowledge the help of the students who did most of this work. So the ones over here are former students, the ones below are current students. The names in white contributed to the first part of my talk, and the ones in yellow correspond to the second part of the talk. So thanks a lot for your attention, and I'll be happy to answer any questions.
Thank you, Professor, for the rich presentation. We now open the floor to questions, and anyone can just open up the mic and ask, or put a question in the chat and we can read it for the professor.
Can I ask? Escobedo, thank you for this very nice presentation.
Welcome.
It's a lot of new results and very interesting results. And I'm impressed about the phase diagram in the first part of the talk. I wonder, two questions. I wonder how many minima that you may have in free energy for this kind of entropic driving phase diagram. And if it's true or not, it's a local free energy that you may have, and how difficult it is to deal with this. And if you have an idea about kind of mean field model that can deal with these complex entropic contributions.
Yeah, I think that's an excellent question. So I mean, two things I would say is that in some ways we constructed this model to be coarse-grained so that it would be easier for us to map these phase diagrams and compute these free energies and test some of our ideas about what optimizes different kinds of crystalline behavior. And so if I were to have a more complex system with more complex interactions, so that will basically make the optimization multidimensional. So in this case, for example, now it turns out that it's a lot intuitive to know how to optimize the energetic knob. So if you have energetic parameters, you can almost anticipate, oh yeah, I need to make this stronger or weaker. It's much harder to optimize the entropic knobs because sometimes it's hard to predict, so maybe I can show you this. So in this example, say, I couldn't tell a priori. Look at the zeta value, this saturation for these three systems, these two up here and this one over here. Those values I couldn't have really anticipated. Now, the only case where I could anticipate was the one over here, because it was so simple, geometrically, this simple cubic lattice, they have to fit perfectly in this compound state. So in this case, I kind of knew that for that to be the case, the diameter of the sphere should be the same as the edge of the cubes. And indeed, our calculation shows that that's the optimal value. But if now you have interactions that are more complex, so whatever characterizes any asymmetry in the entropic interactions will not be just a scalar. So probably this zeta will be zeta 1, zeta 2, zeta 3. So that implies a multidimensional optimization. So I see that as being perhaps numerically one of the challenges that you'll have to do this multidimensional mapping. It's doable for 2 dimensions. It's very doable. We have done it, but so clearly will become more taxing if you have more variables there. I think that that I think addresses one of your questions, but I think I'm missing the second part.
Can you, like this phase diagram, very complex one for octahedron?
Yes.
Do you think that you may have some mean field model that can
yes.
deal with these very
Right.
complex phase diagrams?
So something we've been doing is looking at mean field models have been used for spherical components. And for that, there are some good theories, cell theories that make some good predictions for phase diagrams. And I think that those will be excellent systems to, in some ways, test to what extent those theories, the prediction they made about the coexistence free energy corresponds to, say, a simulation model and the optimal behavior for a particular system. Now, for systems where you have the polyhedral component, I think that there is not. So we looked whether there was some suitable theory for this particular system, and at least at the time there wasn't. You can do some kind of mapping in some lattice models where you would say, well, it's a lattice model where it has some particular symmetry, based on the bonding coordination that you expect them to have in the crystalline state. But they will be very approximate. So I think that as far as good mean field theories that include polyhedra of arbitrary shapes, that's still not very developed, I think.
Thanks.
You're welcome.
Oh, Professor Elliott has a question. You can read it. You can ask yourself to Professor Escobedo, Elliott.
Okay, I'll try. So actually, there's 2 questions. The first one is probably something simple, I just don't know. So for the octahedra plus cube phase diagram, where you discovered that rotator phase, how did you discover the rotator phase? Did you look at simulated X-ray scattering spectra and then it just looked different, or?
No, I mean, interestingly, this is a prediction. So experimentally, people have realized the compound, so this compound phase, because they use energetic interactions via this complementary DNA. And so that corresponds to basically, let me just show you this. So this case, the one below, that has been studied experimentally, at least for one case that corresponds to our phase. But not this R phase. The R phase is, as far as I know, has not been confirmed experimentally. So the way we found it is just, so when you use this phase coexistence mapping, so it's something like a Gibbs-Duhem integration that we have a sort of a fancy way of doing it that we call the Phoenix method. But you basically start by knowing the phase coexistence of the pure components. So in this diagram, you will start with, say, this point over here, and this point over there. And then you will start So if you are starting with a pure octahedra, adding spheres. Now you do that in a sort of semi-grand canonical ensemble, or a semi-grand NPT ensemble. And so as you start mapping this coexistence, you start sort of discovering the phase diagram. And at some point, you will see that all of a sudden, we went from having, say, this coexistence to this other coexistence, where the system changes from being the isotropic phase into becoming this R phase. And likewise, you do it from the other side. And a good confirmation is that the results from the integration coming from one end or the other should agree. And so in our simulation, we make sure that that's the case. But so this R phase just, we didn't know about it, just appeared as we were doing our thermodynamic integration.
Well, how did you recognize that it was appearing? You've just got atoms in a box. And so you have to count the atoms somehow, or the distances between them, or something.
Yeah, I think that the first indication was that when the phase became to be, say, non-isotropic, when we were doing, say, this mapping over here, so the integration was going haywire. So there was something about that phase, the property of the phase, the density, and it's a semi-grand canonical ensemble. So there was also something about the composition that was, so things were changing in a discontinuous way. So that forced us to re-examine whether it was just some issue with the simulation, or what's happening with the phases. Now, sometimes you have like these phase reversals, where say what is supposed to be isotropic became Minkowski, or what was supposed to be Minkowski became isotropic. But so you analyze it through order parameters, just to see, is there any orientational order? Is there any positional order? And we found that it was forming this phase over there. Now,
okay, so some order parameters. Okay.
Yes. We also confirmed this by just creating an interfacial system. So you can create a system where you start with the two putative phases, and you want to see, are they going to mix and form this R phase? So we thought, if this is an artifact, if I start with a system that phase separates between an S phase and an M phase, then they should mix. And indeed, when we put in one box the two phases S and M for the equimolar composition, we found that they didn't want to stay phase separated. They mixed and formed this R phase. So we tried to get it from multiple angles to make sure that it was a true prediction and it was not just an artifact.
Okay, I understand now. Thank you. So the second question was, if I could go ahead and ask a second question.
Sure.
Okay, so
sure.
So at the very end, you kind of talked about the imposing a structure and then put that as a gradient, as a field for a gradient, and then the molecules would kind of move to that, and you could integrate that way. So I thought, and maybe this pertains to the molecular design concept that you mentioned at the end. So if you knew what kind of structure you want, which it sounds like you do for your, optimal ion conductivity, then you could have just imposed that structure as a gradient and then optimize the molecule to minimize the free energy relative to that gradient, like change the chain length or something like that.
Yeah, I think that that idea goes along with some of the things we are trying. But so I guess to clarify, when we use this method, say the one I'm showing here, so this structure is something that forms spontaneously. So we don't anticipate this based on the molecular design. We have the molecule that happen to sometimes give this shape, this phase, but not uniquely this phase. Sometimes could give some another phase. So this was meant to discriminate between the stability of the phases. But once this structure formed, then you can use the geometry that you see to create an artificial field for this process, for this thermodynamic integration, and avoid basically this hysteresis loop. So that's a different different constraints, I guess. No? But so what you are saying, I think that we feel it will work fine in the context of coarse-grained systems, where you can do something what you are suggesting, that I have this phase I want to form, and I can start modifying the force field basically not to match that. The part that we find will be more challenging is once you go from the coarse grain description to the atomistic description, because so something that is stable in the coarse grained model may not be stable in the fully atomistic model, and that's where we are still trying to figure out the best way to do that.
Oh, okay, thank you.
Welcome.
This is Charles speaking. I have a question.
Yes, go.
Sure, sure.
Okay. Fernando, thank you very much for this presentation. It's a very sophisticated work.
Thank you.
I have a question about the first part. Have you ever come across a case in which there is a isomorphic transition for the pure compounds? Because like these are very rich phase diagrams. They would be even richer if there were this, if the pure components formed a kind of phase transition. Have you ever come across with this type of situation?
Yes, I mean, we have investigated pure component systems based on polyhedral components, and some of them undergo multiple phase transitions depending on the concentration. For example, they can go from one phase to another. Not unlike, say, if you have rods, they can go from isotropic to nematic to esmectic to crystalline phase, and that certainly adds the complexity of the phase diagram. So in some ways, no, the systems I chose for this study were simple in the sense that there was only one main transition from isotropic to crystal. Sometimes you go from isotropic to a mesophase, something in between, and then to another crystal. We have actually a system where, actually in 2D, it's a system of disks plus squares that has that feature, because if you think about the disks go from isotropic to hexatic and then to hexagonal crystal. And that certainly adds more complexity. We've also tried to do the same analysis as I'm showing here, to finding what's the optimal size ratio and so on. And it's clearly more challenging. So you have no more phases there, more things to worry about. But it's doable, so it certainly makes things more interesting.
Yeah, I've seen some systems where there is this isomorphic transition. If the transition occurs between the solid liquid light transition and the eutectic transition, there is a more rare kind of transition they call metathetic transition. This is something I've never seen in simulation. I've seen experimental results for this, but never seen any simulation results of this metathetic transitions.
Metathetic transition? Okay.
Yes, metatectic. Like eutectic, it's metathetic.
Okay.
I have another question on the second part. On this this thermodynamic integration that you did, including another dimension, lambda.
Yes.
So if lambda is not too big for like a small value of lambda, I believe that there would still be a first order transition. So you have to go far enough in the lambda dimension to not observing this first order transition. So is this right? Have to tune the value of lambda where this delta F2 is calculated?
I mean, two comments will be, so one, there are clearly, so for me, it doesn't pay off to go to a very large lambda because it doesn't really help you. So you just need to have enough lambda that you obtain something that sort of resembles the target phase, the target order you're after. The true structure will really develop once you increase the true potential betas in this case. Now, your question is, it's important because one thing that's sort of missing in the prescription is how exactly you develop the external field and sort of the coupling parameters so that this transition, when you go from here to there, that is going to move the system from disorder to something similar to the other phase, is reversible. So in principle, even if it were, say, first order, but with no hysteresis, it would still be okay.
Okay.
But from our observations, at least for the systems we tried, we don't seem to see a first order transition. So somewhere you start, sorry. My mouse went away. So what you see is that it gradually starts moving into this phase, but it doesn't seem to do it at once, but more gradually. So it's I guess a testament to the way how we are designing this field, that these are Gaussian beats, so they have basically no exclusive volume interaction. They just weakly couple with the rods so that they gradually move more and more towards those regions until they are almost all there in that space. So, and that's, I would say, for any practical application, one has to make sure that if you go from here to there, so you compute delta F1 going forward, and if you do the reverse transition from here to there, you get the same delta F1. So if that delta F1 is not the same, that means that there is some hysteresis and the transition is not reversible enough to really compute an accurate free energy difference.
Okay, thank you.
Welcome.
So do you have any more questions? Anyone else? So
I think it's time to finish, no? To close.
Yeah, let's wrap it up. Let us thank again Professor Escobedo for the presentation and the discussion.